NanoSwimmers, an invisible revolution in medicine. The invisible problem. In the vast universe that dwells within us, deep in the bloodstream and among microscopic cells, processes occur that dictate our life and health. But sometimes, this delicate balance is threatened. Cancer, one of the most feared diseases, is the clearest example of this. Every day, millions of people around the world battle this disease. Traditional treatments such as chemotherapy and radiotherapy have saved countless lives, but their physical and emotional cost is high. These methods do not distinguish between good and bad. They destroy cancer cells, yes, but they also affect healthy cells, leaving patients with debilitating side effects. Modern medicine has always dreamed of a more precise solution, something that could attack only diseased cells without damaging healthy tissue. And that dream is closer than ever to becoming a reality. At Technion, a pioneering institution in science and engineering, a team of researchers has developed a breakthrough that promises to change everything: NanoSwimmers. Scientific innovation. What are NanoSwimmers? You can't see them with the naked eye. They're so tiny that even the human eye can't detect them. These devices are elastic cables just 15 micrometers long and 200 nanometers thick, smaller than an average human cell. But don't let their size fool you. They're capable of feats that once existed only in science fiction. The researchers explain that they chemically attached drug-filled nanoparticles to the surface of green algae cells. The algae, which give these tiny automatons movement, allow the nanoparticles to effectively swim through the lungs and deliver their therapeutic payload to tumors. Nanoparticles are made up of tiny spheres of biodegradable polymer, loaded with the chemotherapy drug doxorubicin and coated with red blood cell membranes. This coating serves a critical function. It shields the nanoparticles from the immune system, allowing them to remain in the lungs long enough to exert their anti-tumor effects. These nanoswimmers can move through biological fluids at an impressive speed of 15 micrometers per second. But what really makes them extraordinary is that their movement is magnetically controlled. From outside the body, scientists can precisely steer them through complex environments like the bloodstream. Imagine a tiny explorer advancing with millimeter precision through the network of veins and arteries, dodging streams, forks, and obstacles, all under the command of an operator who oversees its journey from a control room. The real revolution of nanoswimmers lies in their ability to carry a payload. Equipped with drugs, these devices can directly target a diseased cell, such as a cancer cell, and release the treatment at the exact location where it is needed. This could completely change the approach to modern medicine. How they work and their potential impact. The movement of nanoswimmers is fascinating. Instead of relying on motors or chemical fuels, they move thanks to external magnetic fields that push and rotate them. This not only makes them incredibly efficient, but also safe for the human body. Researchers have designed advanced algorithms to control these devices. Through simulations and laboratory tests, they have managed to successfully navigate nanoswimmers through simulated biological fluids. The precision of their control is so high that they can be guided to avoid sensitive areas and head exactly to the desired target. External magnetic actuation swimming nanobot. The swimming nanobot acts internally through the magnetic field induced by the rotation of a permanent magnet, placed at the end of a robotic arm. The nanorobot is made up of a 2 cm PLA, polylactic acid, capsule-type piece, designed in SolidWorks and manufactured with a 3D printer, which houses 2 button magnets and a helical, fixed, steel flagellum. These magnets are responsible for the rotation of the capsule and, therefore, the movement of the swimming robot. Self-propelled swimming nanobot. The self-propelled bacterial flagellum-type self-propelled swimming nanobot. It is made up of a 6.5 cm PLA capsule, also designed in SolidWorks and manufactured with a 3D printer, inside which houses a small motor, model Pololu micro metal gear motor high power 2218 and with a 298 gearbox. Now, imagine a near future in which doctors can treat a tumor directly in its nucleus, without damaging the surrounding cells. Side effects such as hair loss, nausea, and extreme fatigue could be a thing of the past. But nanoswimmers are not limited to cancer alone. This technology has the potential to be applied in other areas of medicine. They could be used to treat resistant infections, delivering antibiotics directly to the site of infection. They could also repair damaged tissue, carry therapeutic genes, or even unblock clogged arteries. The future of nanoswimmers. Despite their advances, nanoswimmers are still in their early stages. Scientists are working to perfect their design, make them more efficient, and test them in more complex environments. However, the first results are promising, and the enthusiasm in the scientific community is palpable. The challenge of designing and modeling this type of robot lies both in its microscopic scale and in the environmental conditions in which they must operate, environments dominated by viscous forces such as the interior of the blood flow. To solve this problem in the simplest way, the researcher asked himself the following question: what organisms exist in nature that are so small and swim in this type of fluid? Therefore, he focused on the shape and propulsion mechanism of cellular organisms such as sperm, capable of navigating inside the body thanks to the movement of their tail. This technology is still in an early phase of experimentation. In this case, the prototype has been tested by simulating the environment for which an artificial cardiovascular system has had to be modeled. This system has been validated at the Jesus Usen Minimally Invasive Surgery Center through comparative analysis of data extracted from animal organs. The porcine heart was chosen for the tests because of its similarities with the human heart. The impact of this technology goes beyond medicine. It also raises ethical and social questions. How do we ensure that NanoSwimmers are accessible to everyone? What measures should we take to ensure that they are used safely and responsibly? As NanoSwimmers move toward clinical reality, one thing is clear: we are on the threshold of a new era in medicine. An era in which diseases that once seemed invincible could be treated efficiently and in a personalized way. In the future, NanoSwimmers could be a common tool in hospitals, part of a medical routine as normal as an MRI or a blood draw. And while there is still a way to go, the promise of this technology is a reminder of what science can achieve when combined with creativity and determination. From the tiniest, we are creating monumental changes. NanoSwimmers do not just represent a technological advance, they are a testament to human ingenuity and the power of dreaming of a better future. Because sometimes, the biggest solutions are found in the smallest places. Do you think this technology will be accessible to everyone? Leave your opinion in the comments box. If you like this video, don't forget to give it a like, subscribe to the channel and activate the bell, so you don't miss any of our videos.